Hello, my name is Sakit Prajaman Ponchai, number 4 from class 611. So, to start off, the Compton effect. So the wavelength of the X-ray increases after collision. This is because the incoming X-ray transfers some of its energy to the electron after collision, so the electron is scattered. So what really happened after the collision? As the particle model, the incident X-ray hit the stationary electron in the target, and this X-ray would transfer both energy and momentum to the electron. Consequently, the electron regained kinetic energy and momentum after collision and is scattered. The remaining energy and momentum from scattered electron is left to the scattered X-ray. So the scattered X-ray has less energy and frequency, but a higher wavelength than the incident ray, as the equation have stated. E is directly proportional to frequency, and frequency is inversely proportional to wavelength. So the result of this experiment suggests that the elastic collision. We can compare the Compton effect to the physical collision of snooker as a pair work. So the elastic collision gives us the two results: the conservation of energy, which both equal from before and after, and secondly, the conservation of momentum, which also equal from before and after.
Hello, my name is Sanawat Law, number 5 from class 611. The Compton effect suggests that light has momentum. Now, this derives from the fact that in the second experiment here, which is shown, the X-ray photon hits the electron and scatters that electron in a direction and also scatters the X-ray photon. Now, so we can see here the M1 represents the X-ray photon hitting the M2, which is the electron, and both particles will reflect and move in different directions. Now, when this happens, the original M2 electron only changes in light wave, but does not changes in speed, which suggests that the particle has momentum. Now, this can be a problem as photons has little to no mass at all, or basically no mass. So, how can object with no mass exhibit momentum? So this creates a problem as the formula for momentum here, as shown is P equals m times v, or momentum times mass times velocity. So this creates a problem as a proton has no mass, so how can it exhibit momentum? Which creates the duality of light particle light waves, as it is shown that light waves exhibit wave-like particles properties. So we can see in the first experiment, which is the photoelectric effect, we can see that when light hits a solid metal, it bounces off electrons. And in the second experiment, when the X-ray photons hits a target, it bounces off electrons, and however, it does not change the wavelength of the particle, which suggests that it has momentum.
Good morning. My name is Walachai Shaisukaji from class 601, number 6. Next, double slit experiment by Davison Germer. He commented 4 experiments. His objective was to prove the property of light, that it was duality. Focusing on one slit experiment, as we can see here, when electron gun shooting electrons into the narrow space toward the optical screen is created a standard deviation graph, which represent the amount of electrons in the screen. Well, he think that perhaps it might caused by a bouncing of the edge or electron bounce off each others. So he decided to create a two-slit experiment. Well, if the electron acting like a particle, the electrons will clump in certain area of the screen. However, if it was acting like a wave, it's gonna distribute and create the inference pattern in the screen. However, uh, the electron was acting like a wave. So he decided, well, maybe we need to shooting the one electron at a time. So they're gonna not creating a spread because of the electron bouncing off each other. But when he do like this, the result came out to be the same. So he could conclude that it's acting like a wave. But he was so curious that which particles go to which of the slit. So he decided to place a detector on front of the slit and at the back of the slit. The result came out that it was acting like a particle. It's clumped at a specific place. But when he turned off the detector, the result became the same. So what happened? The thing that happened is called observed effect. So first, to explain the observed effects, you need to know that the observation was not passive things. We need to change the system fundamentally. You need to change something to measure it. If we try to change something in the experiment by placing a detectors, it's gonna cause it to change the result too. So when we place a detector at the front or even at the back, it's gonna force the electrons to choose that it should be wave or particles. In this case, the electron choose to be a particles, and it needs to choose between the one of the slit too, which is not the nature of itself. So that's why the result of placing the detector and not placing a detector was not the same.
Hello, my name is Sirad Handrukun. Today I'll be presenting about the Compton effect and double slit experiment. So my part is the part 4. So an introduction. Matter and light exhibit wave-particle duality as they behave as both wave and particles depending on how they're observed. This concept was revolutionary in quantum mechanics and challenged the classical physics theories. Today we are exploring the Compton effect, double slit experiment with electrons, and quantum interpretations from Copenhagen and De Bruyne. So the first experiment is Arthur Compton in 1923. So he scattered X-ray on electrons and observed the wavelength shift. So his setup is X-ray beam directed at the graphene target, and the scattered X-ray detected at different angles and change in wavelength measured. So the results are that light behaves as a particle in photons that transfer momentum to electrons, confirming Einstein's photon theory of light. So, and the equation is delta lambda is equal to h, the Planck constant, over the electron mass times speed of light, open parentheses, 1 over cosine theta. And a double slit experiment has two interpretations, which are the classical wave expectations and the actual interpretations. The classical one is that if light or electrons were just waves, passing through two slits will create an interference pattern, both in light and dark bands. The waves interfere constructively and deconstructively. And the actual, if we place a detector at this slit, the interference pattern will disappear. Instead, we see two bands, as if electrons are particles passing through one slit or the other. So in conclusion, the classic one interprets light as waves, but in actual it interprets as particles or photons. And De Bruyne's wavelength interpretation is that if light waves can behave like particles, particles should also behave like waves, following the formula lambda is equal to Planck constant over momentum of the particle. Comparing that to Copenhagen's interpretations, which represent a probability distribution of where a particle might be, when measured, the wave function collapsed to a defined value. So in the Schrödinger cat thought experiment, until observed, the cat is both alive and dead, which is in a superposition. Alternative interpretations are the many-world interpretation, where quantum event create particle realities, and the pilot wave theory, where particles follow a hidden deterministic wave function. Thank you.